and thank you all. Here in California, we're faced with quite a challenging legislative and regulatory environment. We've got GHG reduction goals to address climate change for 2020, now being debated for 2030. We have executive orders for reduction goals for 2030 and 2050. So a lot of the focus is to drive down the carbon intensity of fuels, the natural gas, and we've already eliminated coal generation. We've eliminated fuel oil for heat and industrial uses. So natural gas really is the remaining fuel outside of transportation, which turns out to be part of the big challenge that California is facing with respect to not just climate change, but also clean air. When we look at energy use in California, and when SoCalGas looks at the use of its product, use is really governed by two major environmental requirements. For many, many years, we've always focused on clean air. We have a Federal Clean Air Act. Our service territory is in both the South Coast Air District as well as the San Joaquin Valley Air District. These are the only two non-attainment, extreme non-attainment regions in the United States. That means we have the worst air in the nation, and we have the strictest air quality rules. And yet we've done quite a great job in cleaning up the air, but we still have a far way to go. And under the federal requirements, by 2032, we're going to need to reduce our NOx emissions that contribute to smog and reduce our smog by about 80%. So that's the challenge in front of us. And then the climate challenge, which has come in since AB 32 in 2008, focuses on a trajectory that gets us to 80% reductions, 80% of 1990 levels, which is almost a 90% reduction of current emissions. When you look at our marketplace, clean air is a primary objective for many local jurisdictions, and climate change is kind of secondary, because people are already feeling the effects of increased asthma, both childhood as well as elderly, as well as higher cancer rates. And so first we look at the clean air objectives. We look at air pollution, and we specifically look at NOx. And 80% of the emissions that contribute to bad air come from the transportation sector. That's the real challenge here. It really isn't gas use. It isn't stationary use. It's not generation and refining and industrial use and residential use. It's transportation uses. And it's also a similar, although smaller share, but a similar pattern with respect to GHGs. But if you look just at criteria pollutants and you look at the chart on your left, on the left side of the screen, you can see from the bottom up, it's all heavy-duty sources. It's heavy-duty trucks. It's off-road construction equipment, ocean-going vessels, locomotives, aircraft, buses. These are the sectors that really need to achieve reductions in order for us to approach clean air. So our first focus is looking at heavy-duty trucks, the single largest source of air pollution. And that's why we've been working with the Energy Commission, the local air agency, and Cummins Westport to develop a truck technology, truck engine technology geared to the heavy-duty sector, Class 7 and 8 trucks, that can really address NOx reduction. And they've developed a near-zero truck that's 90% lower in NOx, a near-zero truck engine that's 90% lower in NOx. We call it near-zero or electric equivalent. And this is really a breakthrough technology. We're calling it a game changer. This is essentially an electric equivalent because the NOx coming out of the tailpipe is roughly equivalent to the NOx associated with generating the electricity if it were an electric truck. And this is really important because the environmental community is solely focused on electric vehicles, electric transportation, and hydrogen fuel cell transportation. And yet, according to the Air District, which conducts an annual technology assessment, this is 25 to 30 years out. Yet today, we have an electric equivalent truck. The smaller engine was already certified by the ARB. Next year, we expect the larger engine that's good for interstate as well as short-haul, heavy-duty trucking to be certified and ready for deployment. This means we have a tremendous opportunity to reduce emissions and in here and now, today, long before the electric equivalent would be available. And when you think about this, what does this really mean? Well, if you think about technology transfer, you realize this isn't just for trucks. This is also for fleets, school bus and bus fleets, but it's for off-road, and it's for rail, and it's for marine. And people ask me, well, is this really happening? And in fact, yes, it is happening. I mean, the truck engines are being deployed. In Southern California, all of the transit agencies are 100% or near 100% CNG. In fact, they're now buying renewable natural gas as part of their transportation fuel. I'll get to that in a minute. But we've got the rail operators now talking to us about where are we going to site liquefaction facilities to provide for the LNG refueling for their long-distance, long-haul rail routes. And we have both ports, the Port of Long Beach and the Port of LA, talking to us about siting at their port facilities a liquefaction facility to produce LNG as a fuel for the marine sector, because the marine sector is asking the two ports, how are we going to refuel when we move from bunker fuel to LNG? So this is real. We're seeing an immediate, a midterm, and a longer-term pathway for natural gas to move into the transportation marketplace. This next slide is something that really was an eye-opener for a lot of the environmental community that's focused not on just climate change, but also on public health, clean air, air pollution, asthma, criteria pollutants is what we call them in the States. And this is a chart that looked at, the red line is the pathway for GHG reductions out to 2050. That's the state agency that under AB 32 is developing measures to bring our GHG emissions down to the target, which is 80% below the 1990 levels. And what we did, working with the other area districts, is, okay, what are the NOx co-benefits that come from this pathway? And that's what the blue line is, the NOx reductions. But the dotted line are the NOx reductions that we are mandated to achieve under federal law, and you can see we fall far short of those deadlines. The reason we fall far short is that red line is a line that tracks the scoping plan, which is the plan that's developed by the ARB and its set of regulations, and its electric focus. It focuses on electricity and deploying electricity as a fuel, and it eliminates the use of fossil fuels and does not rely on natural gas moving into transportation. We see that as the natural gas opportunity, primarily in transportation, but ultimately to be deployed across all sectors. California's climate change is really focused on electrification. And we're saying, listen, you've got to think of gas supply like we thought of electric supply 30 years ago. 30 years ago, electricity was primarily fossil. Yeah, we had some nukes. Yeah, we had some hydro. Today, we're looking at 33% by 2020 being renewable. Well, gas supply we need to start looking at in the same way. It's fossil predominantly, but it doesn't need to be. And over a set period of time, we need to look at decarbonizing our gas supply. And so what we say to the regulators is, look, you're focused on electricity and electrifying all of our energy end uses, but we really need to focus on near zero technology that's electric equivalent that still utilizes fuels and decarbonize those fuels. So our focus is near zero gas technology, near zero transportation technology specifically, and then looking at how are we going to decarbonize gas supply, how are we going to develop green hydrogen pathways and do hydrogen blending and develop our renewable methane feedstocks. Our view is it's not eliminate the use of fuels and focus solely on electrification of all end uses, but it's both. It's not either, it's both. And there are many end uses that are more highly efficient, and from an emissions perspective, it's more desirable to use a molecular fuel than electricity, which, as we all know, also comes from, and here in California, mostly from natural gas generation. We're focused on helping to decarbonize the electricity sector, and when we look at the interest in distributed generation, and we're seeing a lot of that in the marketplace, most of the press and most of the activists talk about solar rooftops, and when they talk about distributed generation, DG, they're really talking about solar. But the fact is there's a lot of natural gas distributed generation technology that is of interest in the marketplace. Advanced combined heat and power application, a lot of very small scale generating technology that matches well with renewables, obviously power generation with carbon capture. But when we really look at distributed generation out to the future, we see fuel cells, microturbines, and CHP being deployed in end-use applications in the same way we see solar rooftop in the residential sector. But we're also beginning to focus on decarbonizing the pipeline and taking the fossil out of the fuel and moving renewable fuel feedstocks into the pipeline. And we first look at the biomethane sector. We look at the waste sector and the human production and agricultural sector as our primary biomethane feedstocks. And ironically, the ARB, the Air Resources Board, is right now deliberating on the approval of what they're calling their short-lived climate pollutant plan. This was a plan that was mandated by law 2 years ago to develop, target a 40% reduction of short-lived climate pollutants, specifically methane, black carbon, and other industrial fluorohydrocarbons. And their focus on the plan really is biomethane, and their focus really is wastewater treatment, landfills, dairies, ag production, and in landfills also focused on our organic waste streams and organic waste separation. So we see this as a real opportunity, and we're starting to see it develop. We've got 2 projects now. One that's moving gas into the pipeline. It's a wastewater facility, and we're working with a waste hauler developing a large digester that will be producing enough RNG, renewable natural gas, to fuel their own fleet of trucks, 500 heavy-duty waste haulers, which, by the way, will also be using the .02 engine. So those trucks will potentially be cleaner than electricity. In fact, a net negative carbon cycle for the fuel for those refuse haulers, but also another 500 of their public street sweeper fleet, and then the rest they're going to move into our pipeline. We see this developing over the next decade as a real source of renewable natural gas supply. But it isn't, let me just go back to that, it isn't just the existing supply, which, as I said, is wastewater, landfill, dairies, and ag. But the ARB also has a biofuels pathway out targeted to the 2030s and 2040s as part of its plan to get to 2050 CO2 reduction goals or GHG reduction goals. And the biofuels pathway essentially is purpose-grown crops for liquid fuels. Well, we see as natural gas moves into the transportation sector, particularly heavy-duty trucks, rail, marine, and then RNG starts moving into that transportation sector, that biofuels pathway will really be a biomethane pathway. There's a lot of study now on what the volumes are. The initial thinking is in California, there's enough existing biomethane resources, landfills, dairies, ag, wastewater, that can allow us to displace up to 15 to 20% of our gas supply. And then we look at the same biofuels pathway that we think is a biomethane pathway out into the future, and we're looking at another 15 to 20% displacement. So that's a very significant displacement of fossil gas with renewable gas supply, up to 30 to 40% reduction. And then we look out into the future and we look at other methods, and in particular, we look at electrolysis, utilizing excess renewable electricity to produce hydrogen. It's called power to gas. What we see in California, and I think the Northwest has a similar situation, is what we saw particularly in Germany and some of the EU nations 5, 6, 7 years ago when they began deploying power to gas technology. And that is, you have a mismatch between supply and demand. You have a lot of solar generation midday, or you have a lot of wind generation at night. What Germany found is they had a lot of wind power up in northern Germany blew at night. They didn't have enough demand to meet the supply, and they had to shut off their turbines. But they didn't want to shut off the turbines to protect the grid, because they wanted that renewable power to meet the early demand curve that occurs early in the morning. And so they were paying Sweden to take the power off the grid, their nighttime renewable wind. And the federal government basically said, why are we making these payments? These are dollars we could use to invest and build a power-to-gas facility, an electrolysis facility, divert that wind power through the water, through electrolysis facility, electrolyzing the water to a hydrogen stream, an oxygen stream. The oxygen is commercially marketable, and the hydrogen essentially is stored energy. And what we're seeing now deployed in the EU nation are about 30 of these projects that are being deployed to manage the grid. It's more grid management than it is energy storage, but it's to manage the grid, to protect the grid from temporal excesses, produce hydrogen and move it into the pipeline. They're moving hydrogen into the pipeline, called hydrogen blending. They're also taking CO2 opportunistically from a captured source and methanating the hydrogen with that captured CO2. It's a Sabatier reaction, and it's an air shift reaction, and you essentially produce synthetic methane. So we're seeing both of those occur, hydrogen blending, injection of the gas grid, and also methanation and injection of CH4 into the pipeline. We're seeing interest in the U.S. in this. Actually, ironically, the Ontario grid operator contracted and built the first, or is in the process of building the first power-to-gas facility in North America. We've just built one as an R&D facility at UC Irvine, University of California, Irvine. It takes excess midday solar off of their microgrid, which serves the campus community. And we're producing hydrogen, and we're moving it into the pipeline. We're now in discussions with University of California, Riverside to build a larger power-to-gas facility that would just simply scale up the technology. We see this as a technology from the midterm out to the long term, but it's then the next phase in decarbonizing the pipeline and moving from fossil natural gas to renewable natural gas. One of the things that's also happening in California is a focus on electricity and electrifying all end uses, and really treating electricity as a fuel to displace dirtier fossil fuels. But when you go down that road, there's tremendous increase in demand, tremendous over-reliance on electricity. The demand skyrockets. The need for transmission and distribution upgrades is very, very significant. What the German Energy Agency has said, their experience in deploying power to gas essentially enables them to diversify their grid and manage the gas grid and the electricity grid together as an energy grid, and move power to gas and gas back to power, and balance the system and store any excess renewables. So you resolve your time of day. We're beginning to talk to the CalISO about how power to gas and the gas system can help protect the electric transmission system. So that discussion is beginning to occur today. So this slide really is just kind of a conceptual slide that shows us the diversity of the gas grid and how it can manage energy storage and manage a variety of supplies of renewable as well as traditional fuels, and move them to a variety of uses: electricity, transportation, traditional end uses. We're talking renewable hydrogen, methanation, renewable natural gas, fossil natural gas, and down below is kind of just a conceptual time frame. We really look at the biomethane resources, moving us towards the 20% threshold. That's our early action. Then we need to develop the R&D on purpose-grown crops, and that's another potential 20%. Then as we're developing that, we also need to do the R&D and commercialization of power-to-gas technology, develop the methanation technology, to really develop an RNG supply portfolio that significantly displaces traditional gas supply. We sat down with economic and environmental consulting firm, did a lot of econometric modeling and emissions modeling. They do a lot of work with the energy agencies, the PUC, the ARB, and the CEC, the Energy Commission, the Air Resources Board, and the Utilities Commission. And we basically said, look, let's look at this approach that I've just articulated here and compare it to an electrification approach. And what's the outcome? Well, you can make both approaches reach your 2050 goal, which is reducing GHGs 80% below the 1990 levels. But if you used a mixed approach where you deploy gas to displace higher intensity, carbon intense fuels like petroleum and diesel fuel and bunker fuel in the transportation sectors, especially the heavy duty transportation sector, and then you begin to capture your biomethane and put it into the pipeline as an energy resource, and develop purpose-grown crops for more biomethane supply, and develop power to gas, we can likely get to the 2050 goal faster, at less cost, and at far less risk. So this was really to demonstrate to the agencies and to the governor that we really ought to be looking at a more complex approach when we look at long-term GHG reduction planning. What are we doing to move all of this forward? We're doing all of the R&D on all of this technology, the heavy-duty technology, the RNG technology, the power-to-gas technology. We worked with the state to develop a natural gas utilization a policy that actually directs the state to move down these pathways. We actually now offer a commercial service, a compression service, to help fleets get into the refueling marketplace, to be able to build their own refueling infrastructure. Compression is the highest cost for them, particularly public agencies like schools and metro fleets, bus fleets. We now have a biogas conditioning tariff. The biggest challenge in moving a lot of biogas and biomethane into the market and into the pipeline to deliver to customers is we've got to make sure that the constituents are right, the heat content is right. It's got to meet the qualities and the specifications of pipeline gas that traditionally flows. That is, we now offer that service to customers. We're offering a distributed energy services tariff. A lot of customers have said, well, I'd like to put in a fuel cell, but I don't know anything about it, and I'm reluctant to operate it. We can now offer customers the opportunity that we'll own and operate, we'll install and operate under contract to them as owner. We have a variety of ways that we can deploy and operate distributed energy services. And we're now looking at LNG, RNG, and power to gas, and how they are either a utility or a tariff service. Do we do liquefaction as a rate-based utility facility to provide refueling to the transportation marketplace? Do we invest in RNG production or conditioning, or do we really just invest in the pipeline extensions to do the pipeline interconnects? Power to gas, who's going to build these essentially gas supply projects? Electric utilities, rate-based electric generating facilities. Should gas utilities rate-base gas generation or gas production facilities? So we're now beginning to move down that pathway. This is really more of a slide for California regulators that really is a touch point on all the areas that we're involved in, the work that these regulators are involved in. This next slide is really just conceptually how do we look at things, and we really focus on transportation, moving gas into the heavy-duty sector, converting trucking and transit, and then looking at rail and marine. Because of federal credits and also state credits from the Low Carbon Fuel Standard program here in California, what we're seeing is that a lot of renewable gas from all over the country is moving into the California transportation marketplace. In fact, the LCFS program has resulted in in 2013, 100% of the natural gas used in transportation was fossil gas, and today we're over 50% is now renewable natural gas because of the economic value of the credits from both the state program and the federal program. So we see transportation creating a market pool for the development of renewable natural gas. We look at combined heat and power and fuel cells being deployed over the next 20 to 30 years, decarbonizing gas supply through power to gas and other opportunities we see as a longer-term venture and opportunity. I do have a couple of additional slides that get into the details of some issues of concern related to methane reductions. That is a high concern here in California for a variety of reasons, as well as more detail on power to gas if people have questions and are interested. But for that, I was told to try to keep it under 40 minutes or so. That's kind of the long-term natural gas pathways that SoCalGas is pursuing. A lot of implications on technology development, a lot of implications on end use and market segments, I think, which are fairly apparent. And I'll entertain any questions from any of you. Thank you.
Thank you, George. If you're willing, we'd love to hear more about the methane part. And while I have you guys here, I hope that you guys will enter your questions into the chat box. If anybody's having trouble with the chat box, please send your questions to me via email. As a reminder, I sent you all an email about half an hour before, and we'll make sure that all your questions get answered.
All right, well, I'm pleased to kind of talk about the methane stuff. I think I need to have, there we go. I'll go through the power to gas stuff. Real quickly, this is just definitions. Power to gas is the term that we use to talk about the electrolysis process. It's really focused on storing and redeploying renewable electricity. Nobody's talking about, gas-fired generator, going through electrolysis. That would make no sense. The idea here is to produce renewable gas. So that means excess renewable, which we are going to have. We're going to have midday excess here in California in about 2 to 3 years. We're already seeing that, and we'll also have some nighttime wind. So the idea is you take your renewable power and you convert it to hydrogen, you put it into the gas pipeline system, you can store it. Essentially, you're turning an electron into a molecule, and you can store it forever. And when you think then about storage, power to gas provides a tremendous opportunity for renewable electric storage as hydrogen, because the gas grid and gas storage fields has tremendous opportunity to store that. And since it's a physical commodity, you store it for a longer period of time, and it's deployable in any form. It doesn't have to be deployed as electricity. It could be deployed as heat or for any kind of residential use. And then this kind of gives you the idea. These are the 4 storage fields we operate, and if you're thinking about the long-term future and power to gas, and as we build out our renewable portfolio and we have more and more time of day mismatch between supply and demand, we're going to rely on more and more storage. And while battery storage may develop, it's very, very expensive, and from a volume and from a scale perspective, doesn't come close to what gaseous storage can provide. These are just 4 of our large batteries, if you will. Those large batteries are connected to a distribution system that can deliver to any consumer in the state, just like the electric grid. This is an interesting chart. The EU nations are already looking at, well, how much hydrogen can you blend into the natural gas system before it's a problem? I think most scientists basically say, well, about 4 to 5%. But if you have a lot of plastic, you can go higher. Holland, you can see, is already at 12% for a federal reg. That's their regulation. But then most of their system's all plastic because most of it's, is underwater or water related. Germany has now moved to 10%, but then they have specifications about it has to be, so far away from CNG station or other large user. We think that, in the U.S., it's probably 3, 4, 5%. Some of the work we're doing on our R&D projects is going to help us validate that, and also then look at what needs to be replaced in the system. But what we do know is you can't get much beyond 15% or 20% before you have a negative impact on most of your end uses, your burners, your generators, and that essentially is a limiting factor that you've got to move to methanation, that's the ultimate direction to go.
Hey, George, we have a question
emission.
real quick. And the question is, how much water does power to gas require?
I actually have an answer to that, and it is in the notes, and it's not as much as you think. Water is very dense. Gas is very not dense, right? We liquefy natural gas to get it into a container to be a refueling canister on a truck, for example. So when you oxidize your H2O into H2 and O2, you get a whole lot of H2s for a little drop of water, right? In a little bit of space. I'm trying to think that if you scaled it to a residential use, that we could provide enough power deployed as hydrogen to power a house with, I think, 1 or 2 flushes of the toilet volume of water. That was what we came down to as a comparison. I have the data, and I can get that to you, and you can share that with folks. But it's not a significant amount of water. The opportunity also is related to desalinization or the use of brine water. California has a lot of produced water, a lot of brine water from ag that's a potential resource. So water is essentially a resource to produce hydrogen, but we're not talking about vast quantities of water to produce the hydrogen storage you need that allows you to store renewable electricity. Another question. Okay. Methane emissions. We've been being hit hard by the Environmental Defense Fund over the last 2 years on methane emissions from the natural gas value chain. There's a lot of focus on production and capture from production fields, focus on gas gathering, processing, transmission, and distribution. We've been part of the studies with EDF and conducted by Washington State University on distribution leakage. There's so much focus, and most people have the sense that the methane is a short-lived climate pollutant. All that methane going into the atmosphere is coming from the gas systems. It's coming from oil and gas production or gas production. And it just really is just not the case. And so this is a chart to really, break down where the GHG is really coming from. And obviously, it's almost 80% of the GHGs, it's CO2 from energy use. Only 8% is methane. And when you break down methane, it's less than 1% that's coming from natural gas systems. Another way to look at it here is that so the methane from gas systems is less than 1% of all GHGs. Methane as a climate pollutant is less than 10% of our GHG problem. But then if you just look within methane, natural gas systems are less than 9% of all the methane. And so this chart really tells us, and this is a California inventory, all that methane that goes to atmosphere, where does it come from? Well, it comes from landfills, and it comes from the dairy industry, and it comes from the ag industry, and it comes from agricultural production and wastewater. Very, very little comes from natural gas systems. What's interesting is the agencies clearly had not a lot of education on this, and the 2 years of studies being conducted by EDF has created a lot of attention that initially was attention and a lot of misinformation, and that's starting to change. The ARB and the development of what I mentioned earlier, the short-lived climate pollutant plan, really on a broad level was able to educate other agencies and agency staffers, other environmental groups, other legislators, that it isn't all, methane's not from the gas system. It's from, the human production and waste stream. That's where the methane's coming from. And that's what this inventory really tells you. And it's nice to see that that's now the focus. Yes, they're going to continue to focus on driving down the methane emissions from the gas sector, but they're also really looking at the other sectors. Now, we sort of did this slide which looks at, okay, well, what are we talking about here? Look at all the emissions, the CO2e emissions, and where they're coming from, and then we ask the question, well, how big really was Aliso Canyon? The Aliso Canyon leak that we experienced last fall and that we capped in February, vented a lot of methane into the atmosphere. And the popular press, it was the biggest, methane leak in the history of the world, and then it was, in the history of California, and then it was the biggest single source of methane in California. And it was a climate disaster that's going to undo all California's progress. Well, when you really look at the volumes, and by the way, we're still working on our volume accounting based on what's remaining in the reservoir and what we believe we've lost from a physical accounting perspective. Nonetheless, all of the agencies and many of the science nonprofits have been out doing aerial and atmospheric detection, and they've all thrown out their own numbers. And pretty much everybody's throwing out, there's about 95 to 100,000 metric tons of methane, so that's about a 2.2 CO2e carbon equivalent. So if you look at that, what did dairies produce? Well, dairies produce about 1 million metric tons. We probably put out about 2 million, maybe more than 2 million metric tons. So that's about 10% of just dairy cattle in just 1 year. So that little sliver there in the black is how big Aliso Canyon was with respect to all the other methane that's going into the atmosphere that nobody really pays attention to until now. So I just thought I'd give you that. In terms of what we're doing, it's, I think, what all the gas utilities and pipeline and producers are doing. We're focused on, what's the best bang for your buck on the production side and the processing side. I know there's, I don't know the progress of EDF and their transmission study. I know they've released the LDC study. We're actually working with ARB to adopt the factors. I understand that EPA recently made a determination that it would adopt the new factors that were established out of the EDF LDC study. So I think we've had a positive outcome. I think the overall message is methane emissions from the gas sector has been in decline over the past 20 years and will continue to decline. And if we're serious about looking for methane reductions, we really need to look at where the methane's coming from and get the reductions from those sectors. And then that feeds back into the earlier presentation. Those sources are renewable natural gas sources. We need to capture that to prevent it from going into the atmosphere. We need to utilize it as a renewable energy resource. That means we've got to move it into the pipeline and deliver it to our end-use customers. We need to do this to achieve California's long-term climate objectives. This is really an argument we make with the regulators. The distribution side, their leakage rate is about 0.5. ARB had different staff saying, ours is double that. But in fact, using the old factors developed by EPA in the 90s and reportable to both EPA and then under AB 32 reportable to CARB, we're at about a 0.3 or 3.1 leakage rate. But based on the EDF study of our system, Our leakage rate on their study is estimated to be at about 0.1%. So way below what the average is for all distribution, and way below what we actually are reporting under our reporting requirements to both the federal and the state air agencies. Further questions?
Well, that's great. Thank you, George. I really